let me pop it in so we don't have to do the actual work. Oh, it's 3 by 4. So let me row reduce. Oh, dang it. Quit. All right. So we'll do null space and column space. So null of A and column. Now, procedurally, we know it's you find the pivots, the columns that correspond to the pivots are the column space. Well, actually, no, that's not true. The column space is just all the columns listed. The null space is what you get after you've ignored the pivot columns within the column space. So let me write column space first. That's gonna. I'll just identify this as V1, 2, 3, and 4. So all right. So if you identify the pivots will correspond with the basis of the column space of A, also known as the rank. All right, so the basis itself would be just the first two columns, V1, V2, which tells us that we're dealing with a rank of 2. All right, now what the null space is the vectors related to the columns that are not within the basis, right? So we have the column space, and we've kind of addressed it in the sense that, very basically, I guess, not really a pun intended, I don't think. Oh, sorry, got another one there. Rank 3. Not too thick. I might as well circle it while I'm there. Okay, so we can identify the rank very easily. You just find the number of pivots within the matrix. That's not bad at all. The null space you get by solving the equivalent homogeneous equation. So if I were to set this equal to 0 and solve, I'd get, x1 equals, what is this, negative 9x3. With x3 equal to x3. Right? So it's always corresponding to the column that is not there, right? So the X3 column, right? So the null space is really just that. It's a solution to the homogeneous. But what does that mean? What it means is through transformation, it's going to shoot you down to the zero vector, right? So that's the null vector, right? So the null space, because remember anything we do, multiplication, everything is all some form of a linear transformation. So the idea is that if you have some sort of operation that transforms you to the zero vector, you're nulling the matrix out, in which case it becomes a null set. Well, not a null set in the sense that you have no solution, but null as in, like, I don't know, like if a European were to use the word null, they're talking about zero. Did I miss the X4? Dang it. Yeah, because you know what, when I wrote, I had it in my head earlier. Yeah, X3 equals X3, X4 equals 0. When I wrote V1, V2, even though I corrected, I never mentally made the shift. Okay, yeah. So, but the key is you get the X3, which is the vector that's related to the null space of A. And if you're looking for the basis of the null space, you got the negative 9, 5, 1, 0. Okay, what else?
And for those space, just like the 5 points as rows. I mean, yeah, the row space.
The row space. Did I put it all in the same one? And I edited it. The row space is easier to identify. I'm just looking to see where I have it. It's, well, I don't know where I wrote it, but it's any row that's not a non-zero row in reduced row echelon form. I just don't know where I put it. Oh. Yeah, okay. Non-zero rows are the basis of row space.
So for that matrix we just did, would it be
So by following the definition, so the non-zero rows form the basis. So we have the base, each of the rows form the basis. The columns containing the leading ones in reduced row echelon form the, oh, well, we already knew that. Yeah, so we're looking for the non-zero, yeah, so it's all of them. Yeah. I think that's actually a pretty good example. Where did I get that example from? Here? That was number 2. Yeah, that would be a good example to have under, because I think all of these examples had something that had a 0 row. So I would take that as a typo. It's not really a typo. Use example 2 on page 81, also on page 83. Yeah, I think that would be a good one to talk about, because all the rows are non-zero, so it's kind of a good one to address. All right, anyway, all typo discussions aside. All right, what else? That's awesome. It's a great moment in my life. Okay.
Does linear transforming the matrix of an eigenvector correspond to a transformation in the original base vector?
Linear transformation in an eigenvector correspond to a transformation in the original vectors?
Yeah.
Not necessarily.
Okay.
Because the eigenvectors are vectors that are imposed upon the original matrix. They're not necessarily related to the original matrix in that way. So they could, but then they might not.
For like a Markov chain problem, are we gonna have to do like a stochastic matrix to figure out?
Like actually build a matrix?
Yeah.
Nah.
Okay.
Yeah, I think the only thing I could say about it is I think you won't mind the Markov chain question that's on the test. It's under the category of a gimme. Which reminds me, I gotta re-record some stuff in a few minutes. But we'll do that. What else? What else?
Should we know the calc problems really well and the least squares?
You should know how to do both. Yeah,
Yeah.
yeah. They're both going to be on there. Just flat out say it. I'm not going to put both a derivative and an antiderivative, but one of them's going to be on there, and there will be a least squares on there.
Will the question be in chronological order?
For the most part.
I thought of 8 or 10 questions.
Okay.
And
Because there's more gimmies on this one than previous ones. Less
and
work.
the other one, like I've only like royally messed up 2 questions, but it like negatively affected my grade.
Yeah, royally will do that.
Yeah, like Cramer's rule for the 2x2. That was stupid. I don't remember ever learning that we couldn't stop, but we never did do it, so I didn't really connect the dots for that. But 11, 15 or 12?
For the start of the test?
Yeah.
11:15.
Okay.
Yeah.
Cool.
Oh yeah.